Um, okay, so let's continue then. So we're going to today talk about joint distributions. So basically how random variables kind of move together in a way. And so mostly we've been talking about one variable, one random variable at a time. They're interesting questions. Often, like interesting questions that probably are often about several random variables at once. So you have a portfolio, for example, of multiple stocks, and they have different returns, and how these returns are related would affect the performance of the portfolio. Or if you have a patient, the various different characteristics like height and weight, blood pressure, and so on, they're related, and they kind of vary together. Or if you have two servers, for example, if you ask, for example, about the slowest of the two servers, for example, that's something about their joint behavior. So we want to talk about joint distribution, and we talked about it for both for continuous distributions and for discrete distributions, and we'll talk about conditional distributions as well. And we're going to talk about why the marginals, the so-called marginals, are not enough. Hopefully, this will become clear. What a marginal is will become more clear as we go along. Then we'll talk about covariance, correlation, and the two statistical applications of this. We already have seen covariance, and basically we revisit it, and then kind of talk towards the end a little bit about multivariate normal distribution. Okay, so what is a joint probability distribution or joint distribution? Um, like intuitively, if you have two random variables, the distribution is like a distribution of the mass over the plane. So it's like how mass is spread over the plane, and by mass we mean like a probability mass. So this is an example where um, we have x and y that are jointly normal, and each one marginally, each one is standard normal. So what it means is that x on its own is a standard normal, like distributed like standard normal, and y on its own is distributed like standard normal. Um, but as we'll see, this is not enough to describe their joint behavior. Um, in this case, they have a jointly normal distribution with correlation 0.65. And if you plot their so-called joint density, there's a function that determines the distribution. And this is a bivariate function. And it will assign, basically tells you how much mass is in a little patch. So if you have a patch of length dx in this direction, and let's say length, so this is like a dx in this direction, and the length dy in this direction. So this patch has this area. So this density, the value of the density times the area of this patch, so that's the area of the patch, will give you the probability that x lies in this little patch. So x and x plus dx. And y lies in the y and y plus dy. So it's very similar to the idea of this is called the probability, like the joint PMF, sorry, PDF, probability density function. It's a density function, but it's density per unit area. And so in areas, for example, in this area, in this part, and so the color here is the level of F, because if I wanted to plot, it would be a 3D plot. So in this little patch, there's more mass because the darker color means F is larger. In this one, there's less mass. So it's less likely that you find the pair here versus here. And you can see like there's less probability of finding them here than here, for example. And this kind of shows you they're correlated. So the finding them along this line is more probable than finding them, for example, along this line. Or, um, so they kind of move together in a sense. If you, we'll see, for example, this allows you to determine the conditional probability of y given x, for example. So in short, you can think of the distribution as a way of spreading mass or probability mass over the space. Technically, really, the distribution is this measure that given any set, you map it to the probability that xy belongs to that set. So this whole is going to be a probability measure. So for any a subset R2, let's say, sorry, it should be a subset. So for any A that is subset, any A subset R2, you should be able to tell me what is the probability that X and Y belongs to that set. But oftentimes we write it as the integral of sum for continuous random variable, sum function by variate function over that set, dx dy. Okay, so this is probability per unit mass or probability per unit area. And this is the infinitesimal area. So this gives me the probability that I'm in a little patch of area dx dy, and then I integrate it over a set. So for example, if I want to determine what is the probability that x and y land in this set, that could be A. So this would be A. I'm going to have to integrate the function. So you just basically sum all the probability mass that is here, and that's going to be the probability of xy landing in that set. Okay. Does that make sense? Questions about this? So this thing is still called a PDF, probability density. It's a form of density, but it's bivariate. Question? So similar to the univariate case, this has to be non-negative. And it has to integrate to 1 over the entire R2. If I integrate it over the entire R2, this has to be 1. Okay, we can write it as, if you want, you can write this as integral negative infinity to positive, negative infinity to positive. It's like a double integral. Dx dy is 1. But it also carries the information about the marginals. So marginals are the distributions of x and y alone. So if I suppose I want to recover so the distribution of a single, like x would be this measure again, which can be written as the density of that random variable over B. So the idea is that I can recover this density. So this is called the marginal distribution of X, whereas this is the joint distribution. So if I recover the marginal distribution, I can try to recover the PDF. And this can be done if I have the joint PDF. Anyone can see how we can recover the marginal PDF. So how to recover fx of x given fxy of xy. Anyone knows how, or has a guess? the idea. So the point is that I can write this as the probability that X is in, let's say, B, and Y takes any values in the reals. Okay, so Y can take any value, right? So if I want to use the joint, I would get F XY, X and Y dx dy. I'm going to integrate over B, but then here I'm going to integrate over B. Here I'm going to integrate over or okay, so the set that you're looking at would be B. Let's say this is B in the direction of X, but all the Y's left. Okay, so I'm integrating over this entire set. B, let's say, is an interval. And so this whole set would be B times R. This is like a Cartesian product of B times R. So in order to recover, let's say, the distribution, be able to calculate this, I need to calculate something like that. And if you do this, you can see that I can move this inside. So it would be like integral B first. Let me try to do it because we ran out of space here. Okay, let's put it here. Yeah, so what we want to do is I want to calculate the probability that X belongs to B. So I can write it as the probability that X is in B and Y belongs to reals. Okay, and this is going to be integral that's over B first, and then it doesn't matter the order. So over R, f x, y, xy, dx, dy. Okay, so we have, again, let's say B may be this, might be B. If I want to use the joint distribution, I'm going to just integrate over this. Basically, you can call it a cylinder or whatever you want to call this. It just goes from, in the y direction, it goes from negative infinity to infinity, but the x direction is limited to b. Okay, then I can rearrange. I can write it as b here, integral r, fxy, xy, dx, dy. And then, sorry, I have to rearrange the dy here, dx. So I'm going to reorder the integral. So first we integrate over x here, and then over y. I rearrange first integrate over y over r, and then over x and b. Now this, you can, if you look at it, whatever this is going to be a function of x. And I'm integrating that function of x over b, and it gives me the probability. So this has to be fx of x. Okay. So the density is whatever I integrate over b to give me that probability, because this holds for any b. This has to be the density. So what this is saying is that in order to find the marginal density of x, I have to integrate the joint. Did I integrate? Yeah, I have to integrate the joint over the second variable. Okay. So once you integrate in one direction, then you get the right. So this is going to only give a function of x, and this is going to be the marginal PDF. So marginal PDF. So you can get the marginal PDF from the joint PDF. If I wanted to get the marginal PDF of y, I would integrate over x. Okay, so the proof is something like this. So in order to calculate this, so if you know the joint, I mean, this is a special case. So these basically sets, cylinder sets. Oh. univariate sets, you can extend to R, like put in R2, but by extending it in like infinitely in both directions. So from the joint, you can calculate the probability of the cylinder sets, and if you like write it in proper form, you can see that really the inner integral is it should be the density of the x. Okay, so this is called marginalization. So the density of x you get from integrating out y. The effect is on the plot is what happens is I'm gonna say this is the x direction, this is the y direction. We're gonna collapse um, all the mass in the x direction. Look at this is all the mass at x, and all of it is collapsed to all the mass is going to y when we integrate. There's a lot of moves here. You can see more dark here and here than here. Oh, it doesn't show. Yeah, I think it shows with a bit of lag. But that's what I mean. What we're doing here, going up there, but you add up all of this this point to this point gives you the, okay. So really, you can think of it the marginal as the shadow that this joint distribution casts in one direction. Okay, and in this case, the marginals are all the same. Both of the marginals are the same. Uh, so both have normal density once you collapse it in one direction. When you look at the shadow in one direction, they're normal, but their joint encodes more information. Okay, so the shadow kind of forgets how the mass was arranged originally in the other direction. Okay, so there could be many different ways you can, as we'll see, arrange the mass on the plane that gives you the same margin. Um, does that make sense? That's like the geometric idea of marginalization. In the discrete case, things are very simple. So we talked about this earlier at some point. So instead of the PDF, joint PDF, you have the PMF. So PXY. This is joint PMF. This gives you the probability that x is equal to x and y is equal to y. Because they take discrete values, this is all you need. This is the joint PMF. And then if you marginalize, you're basically summing over all y's. So marginalization is really summation over one argument. Does that make sense? Questions? So the distribution really is something like that, but we either represent it by a joint PMF or a joint PDF. And oftentimes you interchangeably use distribution to refer to these PDFs or PMFs. And sometimes I might say the PMF, like the distribution is this. It's a little bit of a abuse of terminology. That's fine. So oftentimes when people talk about distribution, they would identify the term with a representative. So this is enough to specify this entire measure. And the same here. So this is enough. So I might say they have this distribution or this distribution. But what really, I mean, precise meaning is that they have the density, probability density function fxy or probability mass function pxy. Questions, comments? Okay, if not, let's see an example. This is a simple example. We have a joint PMF here. So we have two random variables. They take values 0, 1. X takes value 0, 1, y takes value 0, 1. And the PMF in this case can be represented by just 4 numbers. So I have to specify what is the probability that x takes value 0 and y takes value 0. That's, for example, 0.1. And similarly for the other cases. Okay, so this table just summarizes the PMF in this case. Marginalization would be summing along the, for example, if I sum along the columns, I get 0.5 and 0.5. This gives me the probability mass function of y. marginalization along this direction, like summing the rows, will give me px. Okay, so the probability that x is equal to 0 is the sum of the probabilities. You can see it's very easily that the probability that x is equal to 0 is the probability that x is equal to 0 and y is equal to 0, plus the probability that x is equal to 0 and y is equal to 1. Right? These two events are disjoint, and the union is this. And so I'm summing these two values, so that will give me this value. Right? So that's the idea of marginalization. So marginal basically give you the row sums and the column sums. And you can see that if I then marginalize this, there's no marginalization. Basically, it has to sum to 1, and in this direction, it has to sum to 1 as well. So that table like summarizes joint and the marginals of x and y. Now the question I want you to think a little bit about is, so once I have this, I can answer any question about the pair. For example, I can answer this question: what is the probability that x is not equal to y, or what is the probability that y is equal to 1, given that x is equal to 0? So think a little bit about it and maybe tell me. I mean, these numbers, and then whether x and y are independent. So all these three questions we should be able to answer from this table. Okay. Maybe let's start with this. Anyone can help us figure this out? Anyone? This should be really easy. Are you on? Yes. Okay. 0.8, since it's the sum of the two pairs. Yes. So basically the sum of these two, either x is 1 and y is 0, or y is 1, x is 0. And so that's exactly the case. So we basically write this as all the possible choices. And so this would be 0.8. How about this? Anyone? Would be easy as well. Point 4, why? Shana is saying 0.4. So this 0.4 is potentially the probability that y is equal to 1 and x is equal to 0. So y is equal to 1 and x is equal to 0 is 0.4. But this is more than this. So this is that divided by the probability x is equal to 0 by definition. So this would be 0.4 divided by 0.5. So it would be 4 or 5 or 0.8. Right? So are they independent? So 0.5 is from here, from the margin. Are x and y independent? So if you have the join, you can answer this. So they're going to be independent if this factorizes. You have seen this before in terms of the PMF. If this is the product of the marginal PMFs. This has to hold for any pair of X and Y that they can take. If this factorization happens, then they're independent, otherwise they're not. So if you think they're independent, you have to prove this holds for any pair X and Y. So in this case, 4 cases. If you don't believe they're independent, you should show a case where this equality is not true. What do you think? Not infinite. So why? Really easy in this case. So this, because they're uniform, this will have the same value, right? So this always going to be 1/2. It's going to be 1/2 because they all have the same value here. So this side is going to be 1/4. Okay? The probability is x is 0 is 1/2. The same for y, but the joint probability is 0.1. Yeah, so this side is going to be 0.25 basically. 0.25 for any pair x and y, but you see that basically this is never 0.25. So any of these you can use. Um, so this side is either this or that, but this has to be 0.25. So they're not independent. Does it make sense? It's really easy to check in this case. I mean, in a more complicated case, these could be different. Then you have to worry because you should specify specific choices of x and y pairs for this to violate this. But in this case, this side is always this. So right, so you get 0.8, 0.8, and no. This is an example. 0, 0, so violate this. So x and y is if independent, if and only if the density factorizes, okay, into the product of the margin. For densities, it's similar. So if you have the continuous random variable, two continuous random variables, they're independent if and only if the density factorizes. Proving this, so really what independence means is something like this. I mentioned this before. The probability that x is in A and y in B is the product. X is in A times the probability of y is in B. In the discrete case, it's very easy to kind of convince yourself that it's equivalent to the joint factorizing, joint PMF. In the continuous case, it's a little bit more work to argue for yourself because these are infinitesimal, like once you multiply basically dx, dy, this is like an infinitesimal version of this. So this is saying if x is in an infinitesimal interval around x and y is an infinitesimal area, sorry, interval around y, then this identity holds, and from that you get it for any set. Okay. But really, what we want is the same. So the same fact holds in both cases, but in continuous case it reduces to the density factorizing. In this case, it reduces to the PMF factor. Okay. So this is another point. Independent is the one joint that the marginals determine. So if you give me two marginals and you tell me that the two random variables are independent, then because I know under independence the joint is the product of the marginals, that gives me the full behavior. I get the full joint distribution. Otherwise, if you just give me the marginals, that x has marginal fx and then y has marginal PDF fy, and you don't tell me they're independent, I can't necessarily determine fx and y. So given the marginals plus independence is enough to determine the joint because this has to be the product. This is a special case that the marginals would specify. But independence is a very strong assumption. Once you say independence, you basically determine the joint from the margin. In general, they're not. The marginal has more information than the marginals. So this little statement here is that carries a lot of information. Okay? Independence is the one joint that is determined by the margin. Other joint distributions carry more information. If they're not independent, the joint carries more information than the margin. So here, for example, if I told you that X and Y are uniform, so here X and Y are both uniformly distributed on 0, 1. So it's a uniform distribution and this set. Marginally, they're both uniform because they assign the same probabilities to 0 and 1, but they're not independent. So if I assume that they were independent, so under independence, if we assumed they are independent, then we know that the joint would be the product with the marginal. So what I would get here is the table would be 0.25, 0.25, 25, and 0.20. So that's how the joint would be determined in this case. And this joint distribution is different from this. And you can see this has more information. This kind of this is what you get if you assume marginals plus independent. And you can see that the joint is really uniform on this. So in this case, you can say xy is uniformly distributed over this set 0, 0, 0, 1, 1, 0, 1, 1. Okay. So uniform marginals plus independence implies uniform over this grid. But this is not uniform over the grid. Okay, sounds good. Questions, comments? Okay, so this again, reiterate, so a joint distribution, so a joint density is really a function, bivariate function. I mean, in general, it could be more. You can have joint distribution between more than two variables, but here we restrict ourselves to two, for example. And so it's going to be a bivariate function, non-negative, integrates to 1 over the entire plane. The probability that x and y belong to A, you're going to integrate that over that set A. And by integrating one variable out, you do the marginalization. And you have x and y are independent if and only if the density factor is. Okay, so this slide basically summarizes all the important things about the joint density. Here's an example that we can work with. Here we have like it's a unit disk, not disk, just a unit square. And then I'm assuming that the density is uniform on this part. Okay, so if I want to mathematically write it, f x and y is constant over this region, 0 less than x less than y less than 1. So here is a constant. I'm going to write this c, and then 0, right? Okay, so here it's 0 everywhere else, basically. But here it's constant. Constant, if I want to determine, how do I determine this constant? If I'm saying it's uniform over a region, this is the region, it means that the density is constant there. But how do I determine this value? Anyone can shed light on that? You can have any set in the plane. You can say, okay, I'm uniform on this set, which means that the density is constant in this set. But what do I need to do to calculate constant? I need that constant to fully express. How do we calculate the constant? Anyone? you should use this. Okay, you have to integrate f, and the integral has to be 1. Um, so you can do it, but in this case, rate because it's constant when you integrate it, it just gives you the area of this. So it's a triangle, so the area would be 1/2. So I get c times the integral of 1 over that area, let's call this set t over t. And so it gives me c times the area of t, which is the area of this would be 1/2. So I want this to be 1, so c has to be 2. Okay, so the density will be 2 on this triangle. You can use the double integration if you want. You can say, okay, I'm going to integrate first from, let's say, 0 to 1 in the x direction. And if I'm in the x direction, let's say I'm at x, then I can integrate from this point, which is going to be x2. So I have to integrate over this range. Okay, so I have to integrate from x to 1. The outer integral over x, the inner integral over y, and then this is going to be c. Okay, and so I get c integral from 0 to 1, and the inner integral x times y dy, and then dx. So this integral would be 1 minus x, right? And so you'd get, let's do it out here. Change of variable is the same as dx. Okay, by kind of doing a change of variable. C x squared to 1 is CO2. And so it's the same as this. So this has to be equal to 1, and so C is 2. They can really do by calculus. Okay, and if I want to, for example, once I have the density, if I want to calculate the marginal, I told you the joint distribution basically by saying that things are uniform on the terrain. So now I can answer any questions about the pair. In particular, I can recover the marginal. So I can say what is the marginal density of x. Okay, so this would be the integral over y of xy, like f of x and y. And again, you do the same kind of argument. So here I'm going to fix x, and then the integral from over y would be really non-zero over this piece. So it's going to go from x to 1. And here it would be 2 now. The value is 2. So I get from x to 1, 2 times dy. So you get 2 times 1 minus x. And so this is valid for x in 0 to 1. Okay, so if you do the integral, marginalize out y, you see this is basically, if I fix x, y ranges from x to 1. You can see it here as well. You can see it on the figure or from here. So the range of y that this is non-zero or 2 is like x from x to 1. And so you get f of x is 2 times 1 minus x. So it's a non-uniform distribution. If I plot it, the distribution goes 0, and then it collapses to 1 at 1. So that's the distribution, the density of x. The density of y would be similar by symmetry. Again, you can also see, kind of want to understand why this is true. You collapse, all the mass here goes to this point, and this is 0. And as you drop here, more and more mass comes down, and at this point, the majority, like the biggest mass comes down. So it should be true that mass kind of drops. any questions about this type of calculation? It's um, mostly calculus. Okay, so marginalizing gives you something like this. Um, Actually, so by symmetry I mentioned, but like the formula would be different. So be careful about the kind of it's not symmetric because the y would be small. If you look at the mass, y would have the majority of mass at one, whereas the at zero it's it is it has less mass. So that wasn't correct. So the marginal for y, do the calculation, it would be just 2y. The other one would be 2, 1 minus x, that kind of oppositely uh, distributed. So they're not uniform. So marginally, neither x and y are uniform. The question is that are they independent? And it turns out that they're not independent either. Um, the so they would be independent if they were uniformly distributed um, on the entire unit square. To see that they're not independent, late, it's enough to note that if I like look at air, for example, range of the y's that all see, the distribution of basically y conditional on x will change as a function of x. The light doesn't show that. There's a delay here. You see the slide? Or, okay, it just sometimes there is a lot of delay. So I can see it depends on x. Um, can you see me like drawing now? The, there's a huge delay. Um, yeah, so we'll see this later. So if you look at a particular x, so in this x, for example, the range of y is here. You can argue, that we'll see later, that given x, y uniformly basically on x to 1. But because that depends on x, uh, they can't be independent. Um, let's do it here. So conditional distributions are similar and the kind of we can have like densities for them. So if I fix x and then ask about y, we can create a conditional density. So the thing is, this is a little bit tricky because they're continuous. A priori, the probability that x is equal to a particular x is not meaningful. Like it's just zero. But it happens that I have seen particular x, and I talk about the probability that y is set given that zero. Okay, how to find this is not um, is not um, 11 this course because this has probability zero. I can't probability of y is and x divided by x is equal to zero. Um, Again, I'm not sure yet. There's a bit of delay. I can see the delay on the computer. But, do you see a delay? Have a delay between what I talk about and what appears in the slide? Yes, no, no. Okay. Um, yeah. So defining it like this is zero. So it's going to be problematic. But what we really would do is you do similar things that we did with the density. Instead of assuming this, you're saying, okay, I'm going to assume that I'm in an interval x and x plus a little bit, like delta. And so then I can define something like this, or something basically like that. Probability that y is in y and y plus delta, given this, and then you can do the definition of conditional probability. Probability of the intersection divided by the probability of this, and then you replace with, let me do it very quickly. Let me do it quickly here. Quick conditional independence. So let's say I want to compute the probability of y in y and y plus a little bit, let's say delta y, given that x is in little x and x plus delta x. Okay, this I can do because now both have proper values. So you get probability that y is in y and y plus delta y, and x is in all x and x plus delta x, divided by the probability that x is in x and x plus delta x. Okay, now this I can write as using joint density. Okay, this would give me f xy roughly evaluated at x and y, because this is like a little patch at this point times delta x delta y. Okay, this is a little patch. If you imagine, this is like x, this is x plus delta x. This is y, y plus delta y. So we have this little patch here. And if delta x and delta y are small, like fxy is really constant, and the value would be fxy divided xy over this entire thing. So then I integrate basically this density over that region. It's just going to be this same value roughly times, this is going to be approximate, times the area, which is delta x times delta y. Okay, it's like a square. And so that's that. And then below, I just get similarly fx of x times delta x. That's kind of, again, the probability that I'm in interval. You have to integrate the density, and it's just it's just this value roughly, because it's constant over that interval times the length of the interval. And you can see like these two kind of cancel out. So I don't have to worry about this. I can let delta go to 0 and it's still well defined. So that's why the conditioning, when you do the conditioning, it makes sense to condition on something which is like exactly equal to x, because I can make the interval small and small, and this side doesn't depend on the length of the interval. Okay, so you can see this is something which is like this. This has the same flavor as like the intersection. This is the probability of the intersection. It's this divided by the marginal probability, something like that. But they're like in terms of the density times delta y. Okay, and so this is really a form of a density because it's multiplied by that, and so we call this the conditional density of y given x. Okay, and this gives me this probability, and so we really have the conditional density. Now, if I want to, for example, I mean, let's say we always let the delta x go to 0, so this side is really going to be that. And so if I want to calculate the probability that y is in some set b, given that x is equal to x, now I can just integrate this thing. So I'm just going to integrate fy yx b y over that set b. Okay, so this has the same flavor as a density. Okay, so this little argument allows you to justify, like at this level of from a like a elementary course of probability, this is a good argument to show that although when you condition the probability of that even x is equal to x is 0, if you look at an interval and then like the for a small interval, this ratio makes sense and doesn't depend on this. So I can let delta x go to 0, and basically I can effectively condition without running to infinities for continuous variable. And so this gives me the notion of a conditional density. Okay, so the conditional density of y given x is the ratio of the joint divided by the corresponding marginal that we are conditioning on. And if I integrate it over y, this gives me the probabilities of y being an event, given that I know that x is a certain value. Okay. Any question about this kind of argument or the meaning of the conditional density? Was this kind of clear roughly? So derivation, conditional density, and why it makes sense. It makes sense to condition on x is equal to x, despite the fact that it has probability 0. So a priori, it has probability 0, but I'm going to see a value. Once I see the value, I can update the distribution of y. The distribution of y is going to change. And it's like captured by the density, conditional density. So here's an example. So if I know that x is really x0, then if I look at this value here, let's go to this. If I know that x is equal to x0, this is going to be in our case this was uniform, right? So it would be so I know that, let's say we are uniform on, so f x y is 2 if x is less than or equal to y less than or equal to 1. Again, the equalities don't matter. So whether you're 2 on this exact line or not, it doesn't matter, because the integral is like cares about the area, and the line has area 0. So you can redefine it. It's similar to the univariate case where we can redefine it at points. Here we can redefine it on entire lines or anything that has like 0 area. So this is 0 otherwise. So if I know that, let's say this is x0, if I know that I observed x0, then this here would be x0. And you can see that y is going to be restricted. So it's going to be, if y is less than x0, we are in this regime, so it's going to be 0. So that's the top. This part is 0 if x is, if y is less than. Y is less than x0. And if y is bigger than x0 and less than 1, this is going to be 2. Okay, how about this one? This is going to be just what we had before, 1 minus 2 minus, just 2 times 1 minus x. And this holds for any x. So let me do it without the zeros here. It would be clear. Okay, I'm going to, well, so this would be x. And this is always going to be this, assuming that x is in 0 to 1. So what I'm going to get is in the first case, I'm going to get 1 divided by 1 minus x. So this divided by that. So this holds if x is less than, sorry, y is greater than or equal to x, and then 0 if y is less than or equal to x. So the conditional density of y given x will have a jump. So that's kind of the density. This is the conditional density. So it goes from 0 to the point x, and then it jumps to 1 over 1 minus x. Okay. Um, it's still uniform, so you can say it's uniform because it's a density in terms of y, and the size doesn't depend. So the size depends on what x is, but it's uniform over y. So what this distribution really is what we can say is like y given x is equal to x is uniform on little x and y. Okay, so this is saying x has taken value little x, and this density is really uniform on this side has to be less than 1. Um, so this is saying over this region x to 1, this density does not depend on 1, and it's just the area. It's just the area of the line from x to 1. Intuitively, it's also clear from this image, we're going to be restricted once I have x, we're going to be restricted to this line. So it's going to be 0 here. There's no mass. And the probability mass in this interval is like uniformly distributed because things are uniformly distributed in the triangle. There's no reason why this side should be more probable than this side, for example. And so from the figure, it's clear. And also, the calculation shows that y given x is equal to x is distributed like uniform x and 1. I hope this notation is clear. So this is what people use. So this is saying distribution of y, but conditional x being x. Okay, so this changes the distribution. Originally, the distribution was putting this mass. Okay, so this was the distribution. So unconditionally, f of y is not uniform. So y was distributed like fy of y, which was basically 2y for y in 0 to 1. Okay, so I put this mass, but once I condition, the distribution is uniform. And because the conditional distribution given x versus unconditional distribution are different, the two random variables are really dependent. Okay, that's another way of proving. So you can see that if this guy, if this is equal to f of y, this is the marginal distribution of y without conditioning. This is conditional distribution of y given x. If they're equal, then it implies once you equate the two, equate this and this, and then do that, equate the two, and then multiply both sides by f of x, you see that this implies f xy is equal to fx times fy. I dropped the this implies fxy is equal to fx times fy, which is the definition or like the equivalent version of independence. Okay, so independence can be written as this or this. They're equivalent given this formula that we derived. Okay, so this is saying if I condition on x and the density of y doesn't change, it remains the same as the pre-conditioning density, then they're independent. Otherwise, they're not. Okay, so this is kind of equivalent if and only if. Okay, which is equivalent to x and y being independent. So in this case, they're not independent because I conditioned. And by conditioning, I calculated density, and the density turns out to be uniform on x and y, which is also clear from the figure. But we calculated the marginal density. Marginal density is different. Just marginal density goes down like straight. This one never puts any mass here with the conditioning. It's like intuitive because y is always bigger than x. So once you know x, you know that y has to be bigger than x. Otherwise, you need one. And so this proves the independence. Okay. So, and then because this is a density, it has a lot of properties like the mean and the variance. And the mean of this is the so-called conditional expectation. We can kind of discuss this later, but it's a proper density. If you integrate over y, it integrates to 1 because it's just the integral with orienting set is just a probability. It's like a conditional probability. And a conditional probability is a proper measure, which means that the conditional density just integrates to 1 and it's not negative. And it has a mean. So for example, if I look at the mean, there's a mean, which is like integral of y, fy of y, given, sorry, let's do it here. It has a mean, so it would be like integral y, fy of y given x dy. And so this will be the definition of conditional expectation in our case. It's one way of defining it. It's just that the expectation of this conditional density. And it turns out to be like 1 plus x over 2, because it's just that we know that the conditional distribution is uniform, and the mean of the uniform is like a plus b over 2 if it's uniform over a and b. So it's like 1 plus x over 2. We can also see from the expectation, because the expectation depends on x. It doesn't have to, it has to not depend on x, because if this holds, then this is equal to that, and this doesn't depend on x. So the mean of this would not depend on x. The fact that the mean of this distribution depends on x is another indication that that they're not independent. Okay. Really intuitively, what happens is that, let's say if I know that x is here, it's a very little range of x. If I know that x is 1, then y has to be exactly 1. There's no other choice. Whereas if I know that x is 0, y is like wildly variable, can be anything. So that's kind of the knowledge of x changes the distribution of y. Sounds good? Questions? Can you pause here? This is like an important slide. So the conditional density differs from the marginal. It's a direct proof of independence. Averaging, or taking the expectation, or the mean of this distribution, allows you to define conditional expectation, which is written like this. And this is also dependent on x in our case. It turns out it's like also the best prediction of y given x in a particular sense, in the mean square sense. So if you wanted to predict y, given the knowledge that x is x, and if you wanted to minimize your average error, the best is this. So your prediction would be 1 plus x over 2. We'll talk about it next lecture. Okay, pause a little bit. Any questions about it so far? So this generalizes to, like, not generalize, but in the discrete cases where it's like easy. So there's going to be a PMF, like conditional PMF. Y given x is just going to be the joint PMF divided by the marginal PMF. You can just do it, just replace everywhere densities with PMFs, and it will be easier because it's just probability rather than density. Just everything carries over to the discrete case. Questions? Okay, so this slide is trying to just emphasize that two random variables can have the same marginals, but under different joint distributions. So here we have x and y that are dependent and marginally standard normal 0, 1. So these are the marginal distributions. And if you draw from this pair, this is the scatter plot that you get. So you get points that are kind of random, but more around 0. And then also you can see it's like circularly symmetric or rotationally symmetric. And roughly what happens is that knowledge of, if I know x, the distribution will not change. It may not be clear here. But, once you renormalize, this, once you normalize by that, it's going to give you the same. So if I calculate the conditional density in this case, it just would be the same as the marginal density. In other words, once I specify their independence, basically f, x, and y is completely determined by the two. Okay, these are marginal normal distribution, like 1 over root 2 pi e to the negative x squared over 2, and this is 1 over root 2 pi e to the negative y squared over 2. So this is going to be 1 over 2 pi e to the negative x squared plus y squared divided by 2. So that's the joint distribution in this, or the joint density, because they're independent. Everything is known. Here's another example. If I define x to be normal 0, 1, and then let y be s times x, where s takes values plus minus 1 with equal probability. It's like a fair coin toss to determine the sign. Then marginally, y will also have a normal distribution. By symmetry, we can prove it. Given like s is equal to 1, y would be equal to x, and given s is equal to negative 1, y would be negative x. Because the standard normal is symmetric around 0, in each case, the distribution would be, the conditional distribution would be normal. So the probability, like, in other words, the conditional distribution of x, y given s equal to 1 would be normal 0, 1. And the conditional distribution of y given s equal to negative 1 would be normal 0, 1. Because it's the same on both cases, the law of total probability tells you that the marginal distribution is normal 0, 1. It's just going to be 1/2 this plus 1/2 that, which is the same thing as a normal. Strom's law of total probability in disguise, basically. Okay, so y will have a marginal distribution the same as x. And so marginally, the two figures are the same, but the joint distribution would look like this. It's going to be either on this line or on this line, because either x is equal to y or y is equal to x. This happens randomly. No other place on the xy plane you can find the pair. So the pairs would be on the union of these two lines. And we'll kind of maybe discuss this. It turns out that the covariance of x and y would also be 0. But they're strongly dependent. And so marginally they're normal. Their covariance is 0, but they're dependent. So this shows multiple things. First, the marginals don't determine the joint necessarily. You can have two random variables that are marginally normal, whose covariance is also 0, but they're really dependent. The reason why they're dependent is that the absolute value of y is the same as the absolute value of x. So if you tell me x, I know perfectly well what the absolute value of y is. I just don't know the sign. It tells me a lot about, like, knowing x tells me a lot about y. And like you can make it into a formal proof. So this example is good to keep in mind. Just marginal marginal knowledge of just the marginals is not enough to determine the joint. We can have many examples. We have 2 examples here, 2 different joint distributions, one under independence, the other under very strong dependence, that have the same marginals. It turns out that this is an example of a multivariate normal distribution. So x and y are bivariate normal. This is not an example. So in this case, you can't say they're bivariate normal. This is not an example of bivariate normal. The second thing is that you can have covariance, which is 0. We haven't calculated it. We can do it shortly. But still be dependent. So this is a key fact, that independence implies covariance 0, but not vice versa. So the other direction is not correct in general. So if you have covariance 0, you could have dependence still. This is the only case where this is not, like, the other direction goes if they have a bivariate or multivariate normal distribution. So under joint normal distribution, the other direction works. But this is an example where you have marginal Gaussianity, um, but they're not jointly Gaussian, and this direction is false. Okay, is this roughly clear what this slide is trying to capture? Any questions about this? So the joint distribution, in this case, we can't actually provide a density in the sense that we actually have here, because the supported distribution has zero area. So it's like on a set, it's supported on a set. It's like an example where you need proper measure theory to actually discuss. But this, the joint distribution in the sense of, in this sense, is well defined. So I can tell you what is the probability that X and Y lies in any subset of R2. I just can't write it as an integral, proper integral, because the density basically would be infinity in these, because the area is zero. In order to multiply a zero, like an area of zero times something to give you a positive probability, the density has to be infinite. So with respect to the so-called area measure, or like the Lebesgue measure, the density would be infinite or non-existent. So this is an example where there's a proper joint distribution, but it's not represented neither by a PMF nor by the density as we know it. So this requires you to properly like study measure theory, like more advanced probability course. You can try to make sense of uh, these distributions. It makes sense as long as you write like don't worry about like integrating the density in the sense that we already discussed. But otherwise, it's like a very good example that it shows a lot of things. There are joint distributions that are not neither continuous in the sense that we discussed nor discrete. Um, marginals don't specify the joint uniquely. You could have zero covariance and still be dependent, and so on and so forth. And marginal being marginally normal does not mean they're jointly normal. We didn't define joint normality, but this is an example that violates that. So marginally normal does not mean jointly normal. I didn't properly define it yet, but it's an example where they're not jointly normal. The joint is really what we care about when you look at the two. Once you specify the joint, you have everything. Okay. Okay, let's do a quick example. If you have questions, let me know. But let's do a quick example. So another point about the joint is that if you have a function of two random variables, in order to specify its properties, probabilistic properties, you often need the joint. So if you have, for example, x1 and x2, if I look at, this is the two random variables, let's say they're independent and they're uniform and 0, 1. This specifies the joint uniquely because of the independence. Then I can ask, for example, what is the distribution of the maximum? Okay, maximum requires you to, maximum x1 and x2 requires you to think about the joint. If I just tell you that they're marginally uniform, it's not enough to determine the distribution. So the question is, what is the CDF and the PDF, or density of them? And then find expectation of it. Maybe you can think a little bit and then tell me what this is. So x and y are independent on uniform 0, 1 random variables. So we want to compute the CDF density and then expectation of m, which is the maximum of it. This is saying like we have two tasks. Each one takes like a uniformly at random time in 0 to 1 to finish, and they're running in parallel. They're kind of independent of each other. What is the properties of the 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 finish time of the two, like the maximum of the two, when we're done with the, you say there's subtask of a bigger task when the final task is done. Anyone can help me like do the CDF? There's some hints here. So let me help you. If I want to compute the CDF, it's like the probability that m is less than or equal to t. I have to figure this out for any t. So this is the probability that maximum of x1 and x2 is less than or equal to t, right? So how do we relate this to the joint distribution? This would be equivalent to the probability that x and y, like I say, these belong to a particular set, which depends on t. But can you determine what the set is? The maximum of x1 and x2 being less than or equal to t, what is that set? T has to be 0 to 1 otherwise, because they're taking values of 0 to 1. This is at most 1. Otherwise, this would be well defined. If t is bigger than 1, this would be 1, the probability. If t is less than 0, it would be 0. So it really matters to determine it between 0 and 1. So what is the set? The set corresponding to this. Anyone? M is that, yeah, so that's what we have. But I want to specify it as a set in R2. Okay, m less than or equal to t implies a particular set. So it implies that x1 and x2 belong to a particular set in R2. Then I can work with the joint. Yes, okay, 0 to t. So this is the same as saying both x1, so x1 is less than t and x2 is less than t. Okay, so in the art, like in the x1, x2 plane, this is basically this rectangle that like x1 could be between 0 and t, and x2 is between 0 and t. And anything in this rectangle would work. Okay, the entire pair is distributed on the unit rectangle uniformly. Okay, the joint density is 1 because it's just a product. So if x1 and x2 would be the product of two uniforms, like 1 times 1, where x1 and x2 both belong to, basically they belong to the 0, 1, to the 2. So 1 times 1 is like 1. So uniformly distributed and 0, 1. And so this is going to be just probably that x1, x2 belongs to this interval 0 to t squared. So this square, like this little square. And so this would be integral over that square of 1 times dx dy. And so it's like really the area of 0 to t squared, which is really just t squared. Okay, if you want, you can also integrate it like by hand, like integral from 0 to t, integral from 0 to t. 1 times dx dy, and do the integral just factorizes into integral of 0 to t dx, integral of 0 to t dy. So you get t squared. But geometrically, it's also clear. So it's going to be t squared. Okay, so this allows, allows you to compute. This is the CDF m basically. CDF of m is t squared if t is between 0 and 1. It's going to be 0. T is less than 0. It's going to be 0. If t is bigger than 1, it's going to be 1. Okay. So how can I determine the density now? What is the density? Density of them. What is the relation between the density and the CDF? I don't remember. we take the derivative. So it's going to be 2t if t is in 0 to 1 and 0 otherwise. Okay. In this range, it's going to be constant. In the both ranges, it will be 0. So outside, it will be 0. So that's the density. Um, by the way, this happens to be the density of y in this example. Remember, the density is y. So this really, it's kind of interestingly, that's the, just think about that. It's the same density as y. What is the expectation of m then? How can I compute the expectation? Anyway, what is the formula here? Integral from 0 to 1 t fmt dt. Yes. So this gives me from 0 to 1, 2t squared dt, which is like, what is it? 2 times 1/3, something like that. Oh, did I make a mistake? Is this correct? I have 1/2 here. Oh no, sorry, 2/3 is correct. Okay. Now, the thing is, let's say if x1 was equal to x2, then the marginals would be the same. Okay, but the joint would be different. The joint would be one of the cases where just we put all the mass on this line. Again, this is an example where there's no proper density because this line doesn't have any area. In this case, m would be equal to x1, also equal to x2, and so it will be uniform. Will be uniform distributed, not like this. And the mean would be 1/2. Okay. So this tells you that you need the joint distribution, not the marginals are not enough. If I say x1 and x2 are uniform, and I don't tell you their joint behavior, you can't uniquely determine the properties of this. It could be like the mean could be this, or it could be this, or any other a lot of other values. Not anything, but like that it would be between 0 and 1. But in order to determine the density or the distribution as well as the mean and the other properties, you need to know the joint. An example of the joint. So, and then basically functions of random variables, they kind of live on the joint distribution, not the marginals alone. So if you want to determine what is the behavior of x1 plus x2, you can do it in this case as well. It's not enough, like the minimum, maximum, x1 plus x2, any kind of complicated operations on the two. It's necessary and sufficient to have the joint distribution. Okay. Questions? Comments? Okay. So let's revisit the covariance. Now we know that we know the joint distribution. Covariance is a property of the joint, and it's really the expectation of this centered random variable. You can see it's a particular function of xy pair, right? So you know that you need the joint distribution. So it's the function. It's like g of xy, right? So it's a function of xy, so you need the joint. So it's a property of the joint for you. And we have seen that we have these two expressions for it. This falls from the linearity expectation. These are used like centered, right? These are centered version, x tilde, let's say y tilde. We did it in the discrete case, but now you should be able to do it for the continuous case. It's the same kind of thing. So if I want to calculate this, I have to, all the things that we discussed for the expectation carry over. So if I want to calculate, for example, expectation of g, xy, I can use the law unconscious statistician. It should be easy to guess for continuous variables. This would be like integral of g lol x y times now the density, the joint density, dx dy. So if you have the joint, you could calculate this expectation using the law of unconscious statistician. Arguing with, we did it for the, we proved it for the univariate discrete case, but if you go back, it's easily extends to the joint discrete case. And then for this continuous version, you have to argue via infinitesimal areas. More complicated, but it just carries over. There are better ways of proving this in general. Very believable. So this is like probability that you take value xy roughly, and this is the value xy. So you're just summing up these with the corresponding probability. Okay, so if I want to, from the joint, calculate the covariance, I can. But there are other properties. So there's like from this, it turns out that covariance is bilinear. Like the expectation is linear. Covariance is a bilinear operator, which means that it's linear in each argument. So if I do ax plus by and a and b are constants, then this factors like this, or like distributes basically. Doesn't factor, but distributes. And it's the same if you do it in the second argument. So for example, if I do ax plus by and then c z plus d, I don't know, w, then it factorizes, or it behaves like you're multiplying. It's as if you're multiplying to, let's say if I multiply these, how does it behave? It behaves similarly. So if I multiply this, I get ax, ac xz plus ad xw plus bcyz plus bd YW, right? So you just distribute. So covariance behaves like this. So you can just just say this is covariance of x, ax plus by, and then cz plus dw. If you want to determine this, it's just the same thing, but just you replace this with the covariance. So the coefficients are exactly the same. But here this will be covariance of x and z plus covariance of x and w plus covariance of y and z plus covariance of y and w. So intuitively, just imagine you're multiplying things out, but instead of the products, you have the covariances, and that's exactly like the similar here. So as if you're doing ax plus by times z, what you would get is axz plus byz, and you can see this translated to this form. Okay, so this means bilinear. Bilinearity is linear in both like both arguments. And in particular, the covariance of x is also like variance of x. Covariance is kind of symmetric as well. This is also another covariance of xy is equal to covariance of yx. So given these properties, you can do a lot. So covariance is symmetric, covariance of x's is the variance, and then covariance is bilinear. For example, this allows me to calculate the variance of sigma xi, from 1 to n. We did it last time. Or just we didn't. So this proves that the proof of this follows from this definition. And then it extends to actually many variables. So if I want to do the covariance, it's really the covariance of sigma I from 1 to n xi. And the same thing, but I'm going to change the index to be precise. It's the same thing. Okay, covariance of this is a variable, let's say m or s. This is the same thing. So covariance of s and s is the variance of s. I'm using this property. And then using bilinearity, this basically just the sums come out, both sums come out. You can pull sums out and you get covariance of xi and xj. Okay, and then you can write it as over the diagonals, the cases where they're the same, you get the covariance of xi and xi, plus all the other cases where I is not equal to j, uh, but they're between them. So you get these pairwise covariants. Okay. Here you get xi, xj, variance of xi, xj. Okay, and this is really the variance of xi. Okay, so you get the sum of the variances, but then all the sums of all the pairwise covariants. And this follows from the bilinearity of the covariance. And so you get this formula. Variance of the sum is the sum of the variances plus these. So if all the pairwise covariances, these are the pairwise covariants. If all of them are 0, then you get the variance. So the sum is the sum of the variance. We have seen this before. But if one of them is non-zero, then they're going to be there. Okay. So if all the random variables are independent, these are going to be 0, and then you have the identity, the variance of the sum is the sum of the variances, but in general, that's not true. And you don't need independence, you just need uncorrelatedness. Uncorrelatedness means so the random variables are pairwise uncorrelated if these pairwise covariances are 0. And we saw, or we argued, that two random variables can have 0 covariance. Um, 0 covariance, but they're dependent. So let's do this calculation here. Let me show you why. Let me do it here. Let's prove. So I have y is equal to sx, right? S is, let's say, Bernoulli, we call it Bernoulli plus 1, minus 1, sometimes called Rademacher. It's just a random variable that takes values plus 1 and minus 1 with equal probability. Rademacher random. So it's just like a random sum. And I want to compute the covariance of x, y, right? I can write it as the covariance of x and sx, but I can't use bilinearity. I can't pull s out because it's random. It's not constant. But I can write it as the expectation of x times y, which is sx, plus, or sorry, minus the expectation of x times the expectation of sx. That's the alternative formula. Okay. And we know that x is normal, means 0 and 1, and so this is going to be 0. Okay, so I don't have to worry about whatever this is. This is also going to be 0, but this is going to be, the entire thing would be 0. Okay, I just need to figure this out. So here I'm going to get expectation of s times x squared. And I didn't tell you here, but here we're assuming that s is independent of x. Okay, so in order for me to be able to tell you the joint, I have to specify what is the distribution of s relative to x. Let's say s is independent of x. The sign is like the sign coin flip is independent of x. So can you now determine this value? What is this value? How can I calculate this if I know s is independent of x? Anyone remembers if a feature of expectation then apply to functions of independent random variables? So let's say if x and z are independent, what happens to the expectation of f of x and g of z? Let's say h of x, this is like a function. Anyone remembers? They're independent. Okay. This is going to factorize under independence. Expectation factorizes like this. So this would be expectation of s times the expectation of x squared. This is going to be 1, but doesn't matter. This is going to be 0 because it's a random sign flip. It just takes value. This is really 1/2 times 1 plus 1/2 times minus 1. So you get 0. So you can see the covariance is 0. Argue that they're independent. So here, for example, you get the variance. If I look at the variance of x plus y, this holds variance of x plus variance of y plus 2 covariance of xy, because covariance is symmetric. You get covariance of xy plus covariance of yx. You have to look at all the pairs, but by symmetry this holds, but this is 0 in this case. So although they're not independent, we have the variances is the variance. They're kind of this holds. So the variance of this is going to be 2 basically, because each one is 1. So this is an example where the variance of the sum is the sum of the variances, but they are dependent. They're however uncorrelated. So x and y are uncorrelated, but they are dependent. I'll let you argue for yourself why they're dependent. Okay, so that's this result. So under uncorrelatedness, this goes to 0. So a strong assumption is independence. So independence implies this, but not vice versa. Question? We already discussed this, and this leads to the idea of like law of large numbers. We'll come back to it. Covariance is a property of the joint, but the bilinearity of the covariance basically is the main feature that allows you to write this. And the bilinearity follows from this formula. You can just prove this result from the formula. And the linearity of expectation, basically. So if you look at the covariance, and if you normalize it by the standard deviations, the product of the standard deviations, you get something which is always in -1 and 1. This is called the correlation coefficient. So it carries the same information as the covariance in the sense that covariance being 0 tells you something about them being uncorrelated. So covariance being 0 is the same as correlation being 0, but covariance can take any values other than 0, but this is going to always be -1 and 1. So we're not going to prove it, but an example of a Cauchy-Schwarz inequality. Variance of xy is less than or equal to the square root of the variance of x times the variance of y. Another way of saying is that the standard deviation of x times the standard deviation of y. So if you rearrange it, so this is an example of a Cauchy-Schwarz inequality. So you get that the correlation coefficient is always in -1 and 1. If it's ±1, then y would be exactly a linear function of x. So what happens in this case is y would be ax plus b. Actually, probably. Yeah, I believe b is so valid possible. It's like an affine function, basically, with the probability 1. The sign of this would appear in the sign here. But the perfect linear relation would imply correlation being ±1. And again, I may not prove it here, but it's kind of a result to remember. It's like a measure of linear association. So if rho is 0, it does not mean, as we have seen, that the random variables are independent, but they kind of mean that they're not linearly. They can't be like a linear function of one another, or that there's no linear component in the story is a little more complicated, but at least make sure to understand that this does not necessarily imply independence. That example that we had kind of proved this. It's just a measure of linear dependence. They could could have more complicated dependence, for which this doesn't capture, or this doesn't capture more complicated dependence. Okay, that's the story correlation. Let's do this example. So suppose I give you two random variables that are basically the returns of two assets, like two stock prices, for example. You can have some money, you can put all of this in this stock. The other one, like portfolio would be all of it, like 100% on the other stock, or you could like split 50-50%. So you can say, let's say this is the return. So you put one half of your portfolio on this, one half on that, and this would be the return of the kind of balanced portfolio that puts like 50-50% split of your cash. So the idea is that the variance of this portfolio would be, we can compute it. So the variance would be 1/4 times the variance of x plus y. And so it would be 1/4 variance of x plus variance of y plus 2 covariance of x and y. Okay, so let's say they have the same variance. Variance of sigma squared. Then this would be, and then they have the correlation coefficient, which is rho. So this would be sigma squared times rho if they have the same variance. So this would be sigma squared. And then the covariance would be sigma squared times rho. Okay, so I get sigma squared, and two sigma squared rho. So this is what I get. And then if you simplify, you get this expression. So this follows from this result plus the definitional correlation. So what this is saying is, if you have assets that have zero correlation, then the variance of this balanced portfolio would be half the variance of the portfolio that put all the cash on each one. Okay, so you reduce the variance. So you can think of the variance as a measure of risk, how variable your portfolio is, like your return on it jumping up and down. And so you can reduce your variance, allocating half, like 50-50 on two assets that have zero correlation. And in particular, very case happens if you get one, basically if one goes up, the other one changes, this is zero. You have zero variance. So you have neutral portfolio. This is hard to achieve, but on the other case, like if you throw this is going to be a part anyway. Like I said, splitting your money over things that are not correlated is the idea of diversification. So they do it a lot in finance. And if you can find assets that are uncorrelated, and if you spread your money, don't put it all on one stock, then of course this has some implication for your return. You might not get the best returns, but you also could reduce your variance. So a diversified portfolio will have a smaller variance. So in the case where this is zero, you get half the variance of the portfolio. And then if you have more, you can easily see that you have calculated it, like this would be like put over n over n uncorrelated assets, this would be sigma squared over n. And so you can significantly reduce by spreading out over n assets rather than 2 or 1. So n assets with rho I j being 0, I not equal to j. It's like this little side. Okay, so that's an application of this formula in finance. Out of time, but I have two more slides. Uh, we'll maybe come back later next time and talk about it. This is a very interesting case where it tells you like a typical case in statistics or real world where these correlations or dependent structures occur. So oftentimes you have some sort of a like equations involve some hidden variable. So for example, you have measurement certain property like their blood pressure at different times depends on like their state, which could be the same. So given this state, the measurements are independent. Maybe with mean that's given by t, but once more, you get independent, right? Like certain equations um, with latent, don't observe. And I give the graphical ways of kind of independent structure or joint distribution without giving the CDFs or PDFs. So I come back and talk a little bit about this and also a little bit about bivariate distribution. But then otherwise we cover this. I'll stop here. Any questions? Comments? Okay, if not, stop. Thank you. See you next lecture.